So do you have any doubt regarding last class or anything? So this is, I think, 10th week, right? So we have two more week, and I have received that mail. So I see next two class we will do your that cluster expansion and Ising model. That's it. Anything else? What is going on the class right now?
This week I did not follow the class.
Last week.
Yes.
Okay, that's okay. But we have only 2 weeks. So in that 2 weeks, we will do the rest of the part. You have said this Ising model, cluster expansion, these things we will do. I have to read, and now I can read. Now I have nothing. I can read, and next week I will do that. Today I will discuss this statistics part, and then we'll see how this molecular partition function we have this that was discussed in class and also in the previous course, so you know that one.
Yes.
But this part we did not discuss how this molecular partition function and this canonical ensemble partition function, these things are related. That we can prove even that capital Q, let's say canonical ensemble partition function, that is actually q to the power n, that we have used, but we have not proved it. That we will see today.
Yes.
Yes, these things we will see. Okay. Okay, lots of things we have to do today because this was anyway. And regarding your exam goals, I have asked everybody, but problem is it's already 3 4 years. So everyone is saying probably he or she had his they have to find. So I have informed everybody, so they will send. If they have, they will send. Okay. So otherwise, what we can I can ask our juniors because they has more problem to have because they are just past the net or gate, so that I have to arrange. But first I have asked them, so let us wait. Otherwise, I will ask my juniors. Okay. I had everything.
Okay.
Problem I had everything, but problem was my that phone actually lost 2 years ago. So and with that phone, SD card was also there inside the phone. So SD card was also lost, and these things were not backed up. So everything was in that time. That is the problem.
It was not in written form.
Huh?
It was not in written form.
No, it's soft copy. Soft copy.
In your diary where you write this.
No, we have not actually. I used to read from tab. So basically, I use the soft copy. Never I have taken print out or anything. But the class notes are hard copy. That I have written. I shared you know that quantum mechanics notes, thermodynamics notes. That's a hard copy that I have written on my own in notebook. That I still have. Obviously, that's the hard copy I have. These are just formula sheet like na. So I used to read from the tab. That's why I don't have the hard copies of these examples.
If any other notes available, then please send this.
Huh, that chapter wise note I have. That I have.
Okay, please send this.
Which chapter you said? Just inform me. I will. That I have definitely. I have shared you the thermodynamics and quantum mechanics probably, right?
Yes.
Rest chapter, all chapter I have, organic, inorganic, regarding every chapter I have. But that is
Okay,
in
then please
CSI
send.
CSI net standard, not jam standard. So you have to be careful.
Okay, I will read the selected topics from this notes.
Uh, you can't hear actually. Repeat it.
I will read the selected topics from these notes.
Yes, yes. You have to just check whether that is included or in your syllabus or not. Then you can sort.
And the book of Sir Viman Balsi.
Oh, that I forgot actually. Okay, I'm fine. You after the class, you just send me a message. Otherwise, I will forget again.
Okay.
Okay. So is it visible?
Yes.
Okay. So last class we have discussed this, right? This condition we have
Yes.
arrived. Okay. So how we have done this? Mm, Let me start from here. Yes. That there are some conditions like that we know that there are two types of particle, quantum particle and a classical
The
particle.
voice
The
is not clear.
voice is not clear. Actually, I'm connected with my
The
mobile net, so there might be some issue today because my Wi-Fi is not working. Is it too bad?
it sounds like some sound of metal.
Metal. Then 1 minute. Let me turn off my
Ting
fan.
tong sound.
Click on sound. I will not use the headphone. Let's see. Is it okay now?
Yes.
Okay. So probably it may be due to the headphone. Okay. Okay. So in last class we have seen these things that there are two types of particle, quantum particle and classical particle, and classical particles are distinguishable totally. So they follows the Maxwell-Boltzmann statistics, and the quantum particles which are basically indistinguishable. So from this point of we can think about that. Let's say two identical particles are there. This question probably I've asked you before, but still, two identical particles. So let's say they are classical particle, but totally identical particle. So what is the difference between identical particle and distinguishable particle? Indistinguishable particle. What is the difference between these two terms? Can you guess? Hello, hello, hello.
Voice is cutting.
Okay, now is it okay?
Yes.
Okay, I'm asking that. Uh, you have heard about the identical particle, right? In classical particle, identical classical particle. So what is the difference between identical particle and indistinguishable particle?
Identical means all particles same.
Indistinguishables are also right. Let's say you have two ball, classical ball. So they are totally identical, same classical ball. So are they indistinguishable or not?
Distinguishable, we can separate these two.
How? I'm just
Marking A and B.
I'm not marking. Marking A and B it's okay. But actually you are not marking, right? So you have two ball. So how you can, let's say I'm just streamlining your question. The question, let's say you have two ball and two electrons. Both are identical, right? But
Yes.
these are distinguishable, right? Because these are classical particle and these are indistinguishable, correct? Because these are quantum particles. So what is the reason behind this?
The electron has wave nature.
Wave motion, correct. What is the exact reason? You are approaching towards the point. It's surely some quantum features, right?
Yes.
Electron has some quantum feature which that classical ball does not have. That is the uncertainty. Uncertainty in
Okay, uncertainty. Position and
position and
momentum.
momentum means these electrons does not have any trajectory. In classical particle there is a trajectory. So how you can distinguish these two ball? By their trajectory. You can always track
Coordinate.
this ball is this and this ball is that. Okay, let's say you have two
Yes.
same identical ball, but you can always track which ball is ones. But let's say they are electron, they are just um, um, coming and going, means just that is appearing and again vanishing, appearing and again vanishing. It's rapidly. Then can you detect which one is electron A and which one is electron B?
No.
That is not possible because that does not have any trajectory. They have a probability distribution always. Classical particle always have trajectory, and by using that trajectory you can always distinguish those particles. So classical particle may be identical, so never be confused with that term identical classical particle. That does not mean the classical particle are distinguishable. No, they are identical, but they are always distinguishable. Okay, so keep in mind this.
Classical particle are always distinguishable.
Always distinguishable, always. Now this quantum particle, both Einstein statistics and Fermi statistics both can be followed. Which particle are following these both Einstein statistics? They are called boson. Examples are neutrino, photon, phonon, and fermions like electron, proton, positron. These are means the bosons are always multiple of full integral spin, and the fermions are multiple of half integral spin. Mm, Here these things we have discussed that quantum particle always have some wave function psi ab. Let's say psi ab is the wave function. Then uh, if you apply this permutation operator, it will change the position a and b, and it will be psi ba. And from after that derivation you know that uh, there psi ba must be e to the power I phi of psi ab, other there is no other option. Okay, because probability of having particles same. So this is the main condition. So from this condition, you can have only this fact, right? This is only the possible fact. And when the phi is 0 degree, then you will have this condition. After that, using this phenomenon, you just applying this permutation operator condition that if you apply permutation operator two times, you will get back the same psi. So that definitely means that e to the power I theta can take only two value, plus 1 and minus 1. And that means if you uh, insert that, you will have that psi ab will be plus minus psi ba. So if it is plus, then it is totally symmetric, it is bosonic, and if it is minus, then it is harmonic, antisymmetric. Up to this part we have discussed, right? Now today we will prove that for fermionic particle, that means for this antisymmetric case, the occupancy can be either 0 or 1. Can't be more than that. Okay? This part is clear, right?
Voice is cutting.
I'm saying that this part, up to this part is clear.
Yes.
Okay. So today we will discuss this next part, how we can prove that fermionic particle can have only spin occupancy either 0 or 1. That we have to prove. Okay. Before that, let's say you have helium 3. Helium 3 is boson or fermion?
Helium 3 means
Helium 3. Mass number is 3.
fermion.
How and why?
The mass number is odd.
So what?
Number of neutron and proton are unequal.
So what? Helium 2, 3, right? Number of proton?
Yes.
2. Number of neutron? 1.
1.
So, probably you don't know these things you don't have studied, but in electron you know this cell distribution, right? 1s, 2s, these things, correct?
Yes.
In nucleons also, in case of nucleons, there is also the same thing. So when this is 2, that means this will be paired up. It is not similar like the electron case. There is a different rules are there in for nucleons, but if it is even, so you can think that they are paired up. Okay, you can think like that, or you can think like that. This is the option only. These two option. Otherwise, there is no other option. These two probable option, and for
But 2
neutron
cannot be in same direction.
can be in the same direction.
If one is plus up, another will be minus up.
No, 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 no. Let's like this.
Pauli's explosion principle.
Yes, that's I'm saying now. Kind of electron like structure is there. Not exactly same, but you can think like that. So you can see for all three probable cases for this proton case, for every cases, what is the I? I is 0. Here the I is 1, here I is 0, here I is minus 1. Correct?
Yes.
And here I is plus up, here I is
Minus up.
minus up. So total I will be always the half integral. You see,
Yes.
that's why it is fermion. Okay, that's why it is fermion. So this type of question can be asked in jam also. I don't know in jam syllabus that is included or not, but in NetGet they ask basically this type of question. Okay, so now if my voice cuts, then please inform. Okay, then I will go slow. I don't know my
The,
what is the problem with the Wi-Fi. I have to manage with this internet, mobile data I'm using.
okay.
My phone and tab is connected with the Wi-Fi and working properly, but laptop is not connected. it's connected, but then it's showing that no internet is there. I don't know what happens. Okay, let's say now we have discussed up two body system, right? Now let's say if there are n body system means n particle system, these are quantum particle. All are the quantum particle. There are, let's say, n quantum particle. Then what will be wave function? What will be the capital psi? What will be the capital psi? Capital psi will be function of 1, 2, 3 up to n, right?
Yes.
And it is written as psi. Just notice the pattern. A1, psi B2, psi C3, like that.
Z
This
will end at 26, and after that, how I will written?
that is a problematic you can think like, but for two particle it's okay. That's why generally it is written like this way, but that is confusing basically. Sorry, this is confusing, right?
Yes.
That is the problem actually. So you have to give two symbol. What does it mean? That is important. In bracket, that is the particle number. Which particle it is? Okay. And in suffix, that is the particle position. So clear, position or particle state, whatever it is.
Particle state means
I'm coming to that. Coming to that. Let's say you have two particle, then it will be understandable easily. Particle. So this wave function should be written as capital psi 1, 2. So particle 1 A, particle B. Okay. Now, so this is particle 1 and this is particle 2, right? Although there is no tag, all are identical particle, but I'm writing like this. But if it just flips, then what will happen? What will be the wave function?
psi A2, psi B1.
So what does it mean? This position or state is A already. That in that position, it is flipped, right? So it will be 1 and it will be 2. Sorry. So psi A2 in position A or state A, electron 2 is there, and position B or state B, electron 1 is there. Is it clear? So what is state and what is the number of electron?
Yes.
Okay. So you will say this is the case, but it is psi 1 2 again. It is total wave function, so does not it does not nothing with psi a1 or a2. Both it is in both cases it is psi 1 2. Clear? Two
Yes.
electrons are there, right? So both should be psi 1 2. Why I am taking this? Because so now which wave function should you take as psi 1 2? This one or above one or below one? Both are psi 1 2. This is also psi 1 2. This is also psi 1 2. So what should you take as a valid wave function?
First one,
Why?
particle 1 is in the front.
Why you keep the particle 1 in the front? Maybe particle 1 is the state B. Both are probable, right? Both are probable. So that's why the total wave function will be this.
But psi 1 2 is not equal to psi 2 1. It's minus of psi 2 1.
No, 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 no. You don't know who it is fermion or boson.
Yes.
It is quantum particle, I mean. It should be this, na?
Why it's 1 by root 2?
Normalization.
Okay.
This is the coefficient. So if you take the mod square, both will be half half. That's it.
Yes,
These
both will be
things you
half half.
know. These things you know. Let's say you have two wave function phi 1 and phi 2. Then after superposition, total wave function will be c1 square phi 1 square plus c2 square phi 2 square. And this c1 square and c2 square is 1. Correct?
Yes.
These things you know. This is the linear algebraic relation of the quantum mechanics. These things valid. But this is actually if there is another possible condition or superposition, whatever it is. This is okay.
Yes.
So these two are probable cases. Probable wave function of psi 1 2. Okay. Now you see,
In first case, both in same phase. In second case, both are different phase.
yes, that already you have discussed. When you exchange, you are taking the linear combination, right? This and this, that may be plus or minus. Two
Yes.
probabilities are there. So when you are taking two probabilities, you can add or you can subtract, no? Linear combination. That's it.
Yes.
So now, if this is the case, now you see, so what happens? So now you can do psi is, then what will be the 2 1? This is psi 1 2. Then what will be the psi 2 1? Let me write. Just instead of 1, it will be 2. And instead of 2, it will be 1. It is correct?
Yes.
And it is equal to psi is 1 2. Just check. Is it equal to psi is 1 2 or not?
Yes.
Okay. That was our condition, na?
Equal.
So that is the reason why this can't be a valid wave function and this can't be a valid wave
Voice is
function.
breaking.
I'm saying if you choose this as a wave function, then you can't show that.
Voice is breaking. I could not hear.
Okay, okay. Wait. Can you hear?
Yes.
Okay. So I'm saying,
Screen was not visible.
now is it visible?
Yes, now visible.
Okay. Okay. Just inform me when it happens. I will stop. Okay, then. Okay. So I'm
Okay.
saying, if you have this as a wave function, if you take, then you can't prove that psi 1 2 equal to psi 1 or minus 1, anything. Okay, you
I
have to
have to
prove
take
it.
the linear combination.
You have to prove this relation, na? That's why you have to take the linear combination. Then only you can prove that this is okay. This you can prove. But problem is here. Then now you see what will be psi a to 1. Just replace 1 and 2. So you see. So this is clearly minus psi a 1 2. So you need
Yes.
these two condition. You can't prove if you choose any of this as a valid wave function. This or this. In both cases, you can't prove it. You have to take the linear combination. Okay, that's why you have chosen the linear combination of these two probabilities. That is the reason. Is it clear now? So you can't. Okay, one thing, you don't think here this particle are exchange. No, it is as like one can be at a position A, one can be position B. Both things are probable. We have not exchanged the particle here. You have to first understand this one. Here we have not we have psi 1 2. We are determining the wave function, but you don't know where the one will be. One can be here, one can be here. This is a quantum particle, right? One can be in either A position or can be in the B position. Both are allowed. So that's why this can be a wave function of psi 1 2. This can be a wave function of psi 1 2. But the best thing will be if you take the linear combinations. Then you can, and so that for symmetric case it will be equal, and for antisymmetric case it will be minus.
Yes.
So that is the reason. So that's why you have to take the linear combination. So but this is for one particle, right? So see, but for n particle it will be very problematic.
Yes.
So reduce that problem. How you can write it? In order to reduce the problem, this is our wave function. Just see whether you can write it like this. Can you write it?
Yes.
Okay. So for n particle case, how you can write it?
N by n matrix
1 by
root n.
factorial.
Yes, n factorial.
And this will be, what is the rule? Psi a 1, psi a 2 along a row. A is the fix, state is the fix. You have n particle,
Psi a n.
n, psi b1, psi b2, psi bn, and it it should be z. Let's say have z state. I'm just discriminating the subscript and the bracket term. Okay, is it clear?
Yes,
You know what does it call? This is called slatter determinant.
yes, set a determinant.
And in every competitive exam, there is a problem from slatter determinant. It will be there. It is very important thing. Slatter determinant. And this latter determinant will assure you that any two fermions can't share the same state. What I'm saying? Any two fermions can't share the same state. Let's same state means both. Here you see the fermion. This particle one is a state A, and here the fermion one is a state B. Okay. In boson case, you have other options as well. In boson's case, later you will see this is a valid wave function also. Okay. Am I audible?
Yes, the voice was gone for something.
Okay, but okay. This is also a valid wave function, right? Both can be in the same state.
What was the significance of theta determinant?
I'm coming. I'm coming. But you remember for
So the
psi.
word I could not hear properly. That
Okay,
it distinguishes the fermion.
I will again say. I will again say. But before that, you just see for psi 1, 2, these two wave function we have considered, right?
Yes,
But this is also a valid wave function or not?
yes,
This is valid wave function for boson. For fermion, this is not a valid wave function. Why? Because here both particles are in the same state, A. That is not possible. That is not allowed. Why? That is confounded by our Slater determinant. Let's say if state of any two particle become same, then what will happen?
the determinant will become zero.
Why?
Rule of the determinant. If
Yes,
one row
because
is same or one column is same,
yes, exactly. So then the Slater determinant will be, let's say same state they are sharing, right? So A, sorry, this was our normal, but now same state. Both particle are two particles are there. Let's say one or and two particle, they have the same state. So particle one and particle two, if both are sharing the same state, then what will happen? It will be A. So you can write as particle two as particle one. No, no, 1 minute. Both particles are sharing the same state. So 2. Okay, so 2b can be written as 2a. 3b can be written as 2b can be written as 2a. 2c can be written as okay, it's correct. Hmm. Hmm. Both particles 1 and 2 are enjoying the same state. So how do you where the changes will be there? What is the change? What is the change? It's correct. 1 and 2 can be changed. But how it will be 0 now? 1 minute. Okay, okay,
That's
okay.
psi B, psi
Okay,
A.
okay. Hmm. So interchange of any two particles, what will happen then means the interchange of any two columns, yes, if same state, then the will vanish, correct. What will happen, this is for the particle 1, this column is for particle 1, this column is for particle 2, but when you have the same state of particle 1 and 2, then these both column will be equal, same. So if the both column will be equal, you know for determinant case, if the both column are same, then it will be 0.
Yes.
That is the case. In our two particle case also you can see, in that case it will be your psi A1, psi A2, psi B1, psi B2 it was there, but now this 2 it will be again A. So both are A2, A2, so it is eventually 0. Okay,
Okay.
here also you can see as the both column becomes identical, so it will be now 0. So then
Particle can exchange their position, but they cannot occupy the same position. Two
same
particles
position,
cannot
yes.
occupy the same.
You see if the two, okay, let's say this is latter determinant for particle 1 and 2, right? Not 1 and 2, 1 up to n. You just exchange particle 1 and 2, then what will be your latter determinant?
Minus of the first one.
How you can show that, right? What will happen? Just instead of 1 you have to write 2.
First and second column will be interchanged.
Exactly.
C1 and C2 will be interchanged.
This will be your latter determinant.
Yes.
And you know, if you exchange column in determinant, then it is just change the sign. That is the case. Okay.
Will it follow the rule of determinant 100%?
100% because it is a determinant.
If I interchange between three particles, then it will be same.
Yes. Every every rule of the determinant will be followed.
Is this theta determinant valid for bosonic particle also?
No, it is determinant there because there is a negative sign. Determinant gives you this negative sign. In bosonic particle there is a plus sign.
Yes.
So in that case you have to use permanent. Okay. Do you know this?
No.
Nothing. It's easy. You know this A, B, C, D. For determinant is AD minus BC. For permanent it is AD plus BC.
Okay. If I exchange between any row or column, then
Will be
permanent will
same.
be same.
Same. That is the properties of your bosonic particle. So from here you can conclude that so number of particle in ith state can be 1, 0, 2, anything for boson. There is no restriction. But for fermion it is either 0 or 1.
0 or 1 means occupied or unoccupied.
Occupied or unoccupied. No, occupied or or unoccupied or singly occupied.
I could not hear anything.
Means unoccupied, that is a probability, or singly occupied.
Okay.
So you can write it here like that. Clear?
Yes.
So you know what does it call? This principle has a name.
Pauli's exclusion principle.
Exactly. Now, when Pauli gave that, Pauli did not know about boson, fermion, anything. He just gave that exclusion principle as a property of electron, so that you can feel the orbitals of electron properly. You can get the correct combination, and you can reproduce the atomic spectra. He did not knew the symmetry, antisymmetry, these things. This is way later. Okay.
Yes.
Now what we will show for Maxwell-Boltzmann statistics, you know this Q equals to Q to the power n. That we will try to show. This is quite, this is not difficult, but this is quite confusing. You have to just be careful.
This is the most useful statistics.
Hmm? Most useful
Statistics
statistics.
is most useful.
Point is, for Maxwell-Boltzmann statistics only, you can relate this Q with this Q, capital Q and small q. Okay? Only for Maxwell-Boltzmann statistics. So you have seen these things. By using this molecular partition function, you first calculate the small q, and from that small q, you calculate the capital Q, this using this
Please
lesson.
repeat.
I'm saying you have seen that calculating small q, this molecular partition
Yes.
function, and using this formula, you have calculated the capital Q.
Yes.
This is valid for only Maxwell-Boltzmann statistics. For other statistics, you can't do.
I
Okay.
even cannot relate these two, molecular and this individual.
Kind of you can approximately relate. Approximately for bosonic particle. For bosonic particle, approximately you can relate this, but not completely. And for fermion, you can't.
Okay.
So that is the importance. So, so using molecular partition function, that you have calculated the specific heat and these things, you have to keep in mind you are using Maxwell-Boltzmann statistics. That means you are assuming the particle as a classical particle. Although they are quantum
Yes.
mechanical particle, but you are assuming they are distinguishable particle. Means you can think high temperature, so that they can behave
Why
as a,
why the molecule cannot be taken as classical particle?
because they are not classical particle.
Electron and proton they are quantum particle. or the molecule can be
For
treated as
molecule,
classical
after
particle.
molecule, you can, yes. Actually, till now there is no classical. There is perfectly distinguish that up to this length scale, this will be classical particle, and after that it is quantum particle. There is no particular discrimination till now. You can't say. Okay,
Okay.
that is very difficult, very important question, but very difficult question. You don't know. That's why researcher use the field the semi-classical actually. Atom, molecule, solid state. In these cases, not classical, not quantum. They use the semi-classical, and this region is called mesoscopic, not microscopic, not macroscopic. It is mesoscopic. This thing is quite fuzzy.
Mesoscopic.
Yes. Okay, you have not heard about this?
No.
Okay. Microscopic, in microscopic world, quantum mechanics they obey, right? Strictly.
Yes.
Atom, electron, protons, neutrons, these are. For macroscopic world, means our
Classical mechanics.
our world, classical mechanics, correct? But in between these, when you are increasing the length scale, you don't know from where this microscopic world is changed to macroscopic. This means the particles shows their classical behavior instead of quantum behavior. Quantum mechanics become irrelevant, or from where quantum mechanics become relevant, you don't know. So in between scale, basically there we assume there is a mesoscopic world in between microscopic and microscopic. In between, the transition is not very smooth enough, and they are following semi-classical. Where, so in chemistry, this mesoscopic is very important, because this chemical reaction, not atom, basically molecules, these actually lies in this mesoscopic region. So you don't know whether they actually follows quantum mechanics strictly or not. Basically, actually not. They are not very microscopic. So quantum mechanical behavior is there, but that is not very much prominent. Okay.
Classical
Mole
behavior is also there.
Basically, classical behavior you can treat as a classical particles. But now you can approach, there is a two beautiful approach. Okay, these are research thing. I'm just saying you can learn just. You can go up to this mesoscopic world from starting with the microscopic world. Means you are starting considering a molecule as a classical particle, and gradually you are increasing the quantum features on it, so it will become semi-classical. Or from the quantum world, means you are treating the particles as a quantum particles first, and by assuming the temperature is high or the particles are way big, the quantization is less important, you can invoke that classical features. Both are the possible ways, and this way, these things, you have seen that treatment, like when the in case of particle in 1D box for higher levels, it is become continuous, right?
Yes.
These things are basically from microscopic domain, you are going to the macroscopic domain, and this is actually the
Yes.
reverse one. Two approaches are there. So this is called semi-classical. So in chemistry, basically quantum chemistry, this semi-classical treatment is very very popular, and also condensed matter. In case of condensed matter also, solid state physics, condensed matter physics, this mesoscopic treatment is very powerful, semi-classical approach. Okay. So
Okay.
for atom molecule, it is, means it is classical, but sometimes we need the quantum effect like that.
Quantum nature is also there.
Uh-huh. So it is semi-classical basically. So they will here also we'll consider the atom molecules. These are actually the classical particle, means it will follow the Maxwell-Boltzmann statistics. That's the case. Then only you can relate this capital Q and the small q. Otherwise not. Okay. So let us focus now. You know the canonical ensemble, right?
Yes.
So in canonical ensemble, if you remember that our favorite picture, this picture is there. Again, I will copy paste it. Okay. This is a copy of, if you remember, this is a macro state. You have make the infinite number of copies of that macro state, and in each and every copy, the micro state are different, but the same macro state. Micro state are different, correct?
Yes.
Okay. And we have already calculated everything, that partition function, internal energy, everything we have calculated. Now, now we will focus on a particular microstate. Just choose any of that microstate and we will now focus on it. Clear? Voice is
Yes.
clear? Okay. Now we will consider the particles are distinguishable. Here the particles are distinguishable because we are following the Maxwell-Boltzmann statistics. So in this particular for one microstate, for one now forget about the canonical ensemble, forget about the rest of that thing. You are just focusing now on a particular microstate, and in that microstate all molecules are distinguishable, correct?
Yes.
Okay. So there are few energy levels. These are the molecular energy levels. These are not the energy levels of that microstates. That was different. That was E. That is different. That we have already done. That is the energy of that total energy of that microstate, and that was distribution of the energy of that microstate. That is not here. Now we are focusing on a particular microstate. Under a particular microstate, there must be the molecular energy levels. Okay.
Yes.
So these are the, let's say, molecular energy levels. E1, 2, E3, E4, and E up to N. And the total energy of the system is capital E. Let's say E I or E some E. This is the energy of that microstate. The this E we have discussed already. Distribution of this total energy of the microstate. That E,
Yes.
everything. This we have discussed. But now we will be focused on the inside of microstate. Again, I am repeating. Here we are interested of the molecular energy state. These are the energy levels of the molecules. Okay. So
Okay.
now it is possible that there is a more than one type of molecule, correct?
One type of molecule.
One type of molecule means, yeah, it can be mixture of helium and argon gas.
Yes.
Then there is a two type of molecules, right? So it is not necessarily that there is a single type of molecules, or you have just uh, put air inside the piston. Then obviously there are lots of different molecules are there.
Yes.
So there will be a different energy distribution. This is, let's say, for molecule type A. there may be another distribution of molecule B, correct?
Yes.
So this type of distribution can be there. So in general, we can write this is the distribution where this means the jth molecular energy level of molecule
A.
A. Perfect. So now what will be Q? Q you know.
Total partition
Yes, J e to the power e to
minus
J
beta Ej
kBT.
by
Now
kb.
you see, here I am using capital J. This J and this J is not same. This capital J is the distribution of that microstates, and the small j are the distribution of the energy level inside a particular microstate.
Yes, molecular energy level.
So these things are different. So how you can write this capital EJ? This you know, capital EJ should be sum over of EJ sum over of all j, correct?
Yes.
EJB of all j, EJC of all j, and so on.
Yes.
Perfect. This is the total number of total energy. If- Now you can think, it may be all energy state can't be filled up. It may be, you don't know whether the all energy state will be filled up or not.
Yes.
But that is not the important thing here. Important thing is that energy is capital E. When you are writing capital E, that means let's say you have two types of energy, two types of particle, A particle and B particle. That is possible, right? So if you have the two types of particle, then obviously, let's say you have two. Let me write it like this. Just let me reforming these states. Okay, 1 minute. Yes. Let's say this is particle A and this is particle B. Not type. Not type. We can do with the type also, but that is difficult. Let's say this there are n particle. It is particle number A. It is particle number B. Okay.
Yes.
So if that is the case, for the particle number A, just understand it. There all possible energy states are there. You don't know where the particle A is, but this is the distribution, right? Same distribution
Yes.
will be there. So I'm saying you can think like that as well. Let's say particle A is here, particle B is here, C is here, D is here, and so on. N is here. Or
But this energy level are for A.
no, that I'm not. That's the case. No, for all energy molecules, the energy levels are same.
If the molecules are different,
For if the molecules are different, then we can differentiate it. But now let's say if you have the same type of molecule, then it will obviously the energy levels are same.
A number are in E3, B number are in E2. That's like
Means let's say you have some molecule, some types of molecule, let's say oxygen. If it is a different molecule, then obviously the energy distribution will not be the same. Perfect. But for time being, we are considering okay, it is the same type of molecule. If it is the same type of molecule, then obviously this is the energy states.
yes.
And let's say the molecule A you have tagged. There are in n number of molecule you have tagged A, B, C, D, and so on. The molecule A is the energy state 3. Molecule B is energy state 2, like this. C is in the E1 like this. That is possible, right?
A is one molecule or number of molecules, some molecules.
A is A is any one of the molecule. You have just tagged A.
Okay.
Okay. There are n number of molecules. You have just tagged any molecule as a molecule A. That you can do, right?
Yes.
Just think about it, whether there is any doubt or not.
No, in every state there is some molecule.
You don't know in which energy level it is, but any of that energy level.
Yes, it will be in any of the energy level.
Yes. So now, now here EJ, what will be EJ? Let's say molecule A is energy level 2, molecule B is energy level 3, molecule C is energy level 1, and so on. Molecule n number of molecules again energy level 6. This is possible, right?
Yes.
This will be the total energy, obviously.
Yes.
Correct. So you can put it here instead of EJ, you can put it. Just understand it. Correct.
Yes.
But this is for only one microstate. You are focusing on it.
Yes.
But this summation is for all microstate. This is
Yes.
capital. This is capital N. All microstate. Now, for a different microstate, this EJ will be different. Let's say it is now EK. It is now different. A may be in 3, B may be is 1, C may be is 6, N may be in 11. Different.
Yes.
Distribution will be different.
This
For
is for another microstate.
anything, it can be anything. So when you are choosing all the j equals to 1 to n, and you know this is actually capital A. This is it can be goes up to capital A. It's not capital A, but it is a huge number that you know. Correct.
Yes.
So in that case, what you can write? You can write, just see whether you can write or not. And the molecules are distinguishable. You can distinguish which molecule is A and B. That's why you have tagged A, B, C, D. That means it is distinguishable, right? Otherwise, you can't tag them. So
Yes.
you can write this as, just see whether we can write it or not. You can't get it, right? Or is it okay? Just let me write the next step, then it will be clear.
Yes. This is right.
Means eventually for A, it will be all 1, 2, 3. Eventually it will be all, na? For this microstate, A may be in state 2. For another microstate, it may be in state 3. But when you choose the all probable case, all microstate, eventually it will be sum over all I. all possible state. It has to be correct.
Every microstate where the molecule A is in which state?
A is ith state means I is now runs up to 1 2. The this is the molecular levels. Let's say there are 10 molecular level. That I am saying means for one microstate maybe a molecule A in the state molecular state 2. For another microstate is 3. For another microstate is 4.
Yes,
So eventually when you have sum over all j, it has to be all cases, right? EA 1 2 3 4 5 6 7 8 9 10, all you have to concern.
yes,
So you can write it. So that's why the sum can be splitted like this. Now one question you can ask that okay, but it is possible that say EA2 appears twice.
yes,
That thing is possible, right? That thing you can ask. Yes, yes, that is a valid point. You can ask that. But actually, when you have the large number of state, this molecular energy state is also very large. So that probability becomes negligible. That is the
yes.
case.
It's like infinite.
Huh, that is the case. Okay. So eventually what you can write. So you see all are now that same thing actually. It is just particles are tagged like A, B and these things. But particles are the same, right? We have assumed
Yes,
the classical particle, but all are the same molecule. So this is actually the molecular partition function of molecule A, which should be the function of volume and temperature, because this E is function of volume. This is the QB of V and temperature, QC of V and temperature, and so on. Correct?
yes,
So these all things are the same thing, just you have tagged the particle. So it is actually QVT to the power n number of particles are there. So QNVT is eventually QVT to the power n. See whether it is correct or
yes. This is the proof.
not. This is not a mathematical proof. This is just a conceptual proof. Just go through it. I think it is easy. Just you have to think. And you can take
Yes,
a small sample size. Let there is a three particles or like that. A one, two, three, A, B, C, three particles are there and five energy states are there. Then you can prove it. It will not exactly match, but yes.
to match exactly the sample size should be huge.
Should be huge, correct. Now, if the molecules are indistinguishable, then there is a problem. If the molecule size is indistinguishable, then you can't do it actually. This is
Then the n factorial will come.
so yes. So this is the Maxwell-Boltzmann stat considering molecules are distinguishable. But we know for quantum particle molecules are not the distinguishable molecule. They are indistinguishable molecule, right?
Yes,
So in that case, for indistinguishability for quantum particle, this will be the correct form. Okay, but this is for bosons only, not fermions.
can I prove this also?
No, Means you can conceptually prove this, that you are assuming the same part. These are indistinguishable particle, right? So you are assuming the same particle more than one times. You are here when you are assuming this na A, B, C. It may be sometimes the repetition occurs, and that number of repetition is actually n factorial. That's why you have to divide with the n factorial.
How to prove that the number of repetition is infactorial?
That you can't prove, but for using a small sample size, if you calculate, you can see.
Okay.
You have to choose a small sample size. I will send the note. If you are interested, you can go through it. It is a detailed thing. There is, but I don't think this is important here. Okay. I think this part is clear, right? Okay. So, and now this is a problem. You just
I
try
could
to do
not
it.
hear anything.
I have not said anything. Now it is audible.
Yes.
Achha. So try to do this problem. Counting of microstate in Maxwell-Boltzmann, Fermi-Dirac, Bose-Einstein stat. What will be the number of microstate? Try to do it.
At first, Maxwell-Boltzmann statistics.
For first Maxwell-Boltzmann, then Bose-Einstein, then Fermi-Dirac. You have two particles. You have to arrange those particles in three cells. What will be the
3C2.
outcome? Just do it and tell me the answer for Maxwell-Boltzmann, Fermi-Dirac, and the Bose-Einstein.
Particles are distinguishable or indistinguishable.
For Maxwell-Boltzmann, it is distinguishable.
In Fermi-Dirac, it's three-way.
Familiar, it's three. Three arrangements, right?
Yes.
And for both Einstein and Maxwell Boltzmann,
6.
six for six for both Einstein
Yes.
and for Maxwell Boltzmann.
If it's distinguishable, then it's 6.
No, Maxwell Boltzmann means particles are distinguishable.
I am getting 6.
For Maxwell Boltzmann and both Einstein, both cases you are getting six.
For Boltzmann, if I name the particle as A and B, then I'm getting 6. One is
No,
AB and another is BA.
no, no, no. Let me do it. Let's say for Maxwell Boltzmann means the particle are.
Distinguishable, classical.
So let's say we can tag AB, right? Two particles are there, and you have three cells.
Yes. Yes.
Okay,
So 6 is there. Oh, I forgot this. Two particle can occupy same position.
same position. So it is nine. Nine arrangements.
Yes.
This type of question can be asked, right?
Yes. Tricky question.
Tricky question. Bose-Einstein means these are quantum particle.
Indistinguishable. For the 1 1 case, it's 3, and the two particle in one state, it's 3. 3 3 6.
So here, what will be the states? Particles are indistinguishable, right? So both are the same.
Yes.
Let's say dot dot.
And 2 are in same state. That will be 3 case.
Perfect. And what about Fermi-Dirac?
Two particle cannot occupy same position.
Exactly. So only three. Here it is six. What will be another one? This.
In the first case.
So it is three arrangement.
Yes.
So this is the case. Now, one factor is there. This is called xi. This ratio can be calculated. This is the ratio, means probability of two particles Let me write it. Found in same state divided by probability of two particles are found in different state. Okay, then what will be xi here? 3 by 6, right?
Yes.
Half. Here xi will be 3 by 3 means 1, and here xi will be, so for Fermi-Dirac case the
0 by
xi is
3.
always 0. So xi Fermi-Dirac is always 0. Okay, so as xi increase from 0 to if xi value increase, then you can say that it is going from Fermi-Dirac to Bose-Einstein. Okay, that for you see for Maxwell-Boltzmann it is just in between that 0 and 1.
Yes.
So now if I say how you can calculate this, this is we have just taken an example, but in general if I ask, then how you can calculate this count number of microstate. This you know how you can calculate it.
N factorial by n1 factorial and 2 factorial.
Exactly. So for Maxwell-Boltzmann in general, it is number of microstate for Maxwell-Boltzmann where the distribution is ni. Then it is n factorial divided by this, right? Okay. And if there is degeneracy, then it is changes to uh, gi to the power ni. Okay. So for Maxwell-Boltzmann, if there is degeneracy, then it is changes to, this is the number of microstate under some distribution. It is n factorial okay. You remember this formula?
Yes.
Okay.
This is for the degeneracy case.
Yes, G is a degeneracy for ith level. Bose-Einstein, I think this you forgot.
Yes, the only first one I remember.
Okay, but this formula you have to remind
All the three.
all three.
Yes, ni plus gi minus 1 factorial.
So Fermi-Dirac, it is This is three formulas. Okay.
Yes.
So yes, but this derivation I am not doing. There is no derivation properly. Conceptual things are there. How to do this thing that you can go through it. I will share the note. It is there. Okay, I am not discussing the formal derivation. You can show it.
Okay.
Eventually, you can show it. So last thing I will discuss today. After that, it will be finished. Nothing will be there. And the molecular partition function and this using these formulas, the problems we have done already in last class. That I am not doing.
Yes.
It will be repetitive otherwise. Some we can do, very few, but otherwise it will be repetitive. So just last thing we will discuss today, and that is very interesting thing. That is, let's say there is a system. We have seen there is this microstate, and there are some molecules like that, and there are energy levels, molecular energy levels are there. These things we are discussing. But how many energy
Yes.
levels are there? Number of quantum states to us. How many quantum states are available to us? Molecule. That is important. That we will try to calculate.
In very low temperature, only the ground state is available.
Okay, that is sky. But in general, for that, so we can consider these as a for one particle. Okay, we are considering for one particle. For one particle, how many energy states are there? That we want to calculate. So we can think this is a 3D box. Eventually, this is a 3D box, right?
Particle in 3D box.
Particle in 3D box. So you know for particle in 3D box, what is the energy of that particle?
Nx square plus ny square plus nz square by 8 ml square.
Or A square. A is the box length. And this is a square box.
Yes.
And you know this n can vary from 1 to infinity. Okay. And write it as for shorthand notation, you can write it as this. You are just representing it. Okay.
Yes.
For 2D box, if there is only nx and ny, just let's say for 2D box, if it is a 2D box, then you know this would be nx and ny like this.
Yes.
So to plot, let's say nx and n1. These are quantum number, right? So values can be like
Yes.
this.
Principal quantum number.
Exactly. Principal quantum. No, these are just quantum number. This is only was no principal things are there in case of hydrogen atom.
Yes.
Okay. So what combination can be possible that I want to say? Nx and ny. This you know. The ground state will be
0, 0 is not possible.
no 1 1.
Yes. That I'm saying 0, 0 is not possible. 1,
0
1
0 1
starting.
1. This is the ground state. Correct.
Then everything is possible. 1, 2 or 2, 1.
2 1. This can be a state. This can be a state. These points are basically states. And this is the ground state. Correct.
Yes.
And it goes up to this any point. This any point can be there. Each are the possible combination. Okay.
Yes.
And if I just connect like this, then you will see that under this sphere, not sphere, arc, basically these all points are there. These points are not included, but these points are included. Correct.
Yes.
But when this n value is very large, basically you can see the most of the points will be included if the n value is very large. If the here it is 5, if n value is let's say 5,000 or 100, then you will see this value will be very large. Okay. So here you can write what you can write. You can define phi epsilon. This is number of points. Now let's say you are specifying an energy. You want to you want to find out how many points are there with energy En. En, what is En? En is let's say 8 square by 8 m square n square, like that, where n square is let's say 32. Correct. If I want to calculate,
Yes.
that means nx and ny, this is 4 4.
Yes.
That means this point. So you want to calculate how many energy states are there, how many possible combination or energy states are there below this point. Correct. So what will you do? You have to draw a arc like this.
Yes. But the
Which,
maximum point is the 32 for 4 point.
yes, which passes through this. Now see, all points inside this arc will have the value less than En. Just take an random point. If you choose this, here it is
4,
uh
3,
4 3. Oh yes, 4 3 4 3 4
25,
25. So it's perfect. It is 5
4, 2. So, sorry, yes. 5, 2,
5 2, right? So it's
29,
29 less than this 5 3. This is
34,
it is greater than, so it is outside. This is again 5 2.
Yes.
29. So this should be inside. It is due to my drawing error. It should be inside. It's actually consist. So you see, so these all points will be less than en. So let's say this is number of points consistent with an energy. Perfect.
Yes.
So what will be that number of point? What will be that number of point? Just this is the arc, right? So this, what is this? This is the n. You see,
Yes.
this should be the n.
Yes.
And this is the radius of the arc. This is due to my drawing error. It seems like not symmetrical, but it is actually symmetrical. If you draw it with this
Yeah. It's in under root n x square plus n y
scale it
square.
properly, then you can see it. So you can see it will be 1 by 8 of, not 1 by 8, 1 by 4th of
1/4
area
pi n square.
of the circle of radius n. So it
Pi
is
by 4 n square.
correct. And what is n? N you know.
Under root n x square plus n y square.
No, from here also you can write na n square.
Yes.
This you can write. So it is pi by 4 8 m a square h square.
Yes.
So phi e is pi by, oh, it cancel, right? So 2 pi m square en. So this is the number of energy states are there under the energy en. This is, so we can write this is number of energy states. Now one thing you can ask, this is the area, but you are saying these are the number of energy state. How this is possible? Correct.
Yes. These two things are not relating.
These things are related because when the number of energy states are huge, then there will be main points are very congested. That's why.
Yes.
Okay, that's why. Otherwise, you have to multiply a term which is called number density. So here we are assuming the number density is 1. Okay,
Okay.
it is number of energy states available to a molecule. So now you can calculate. This is for 2D. Now in our 3D case, it will be 1 by 8 of that volume of sphere, right? And sphere is 4 by 3 pi n cube, and it will be n cube is 8. This. So it is eventually this. This you can calculate. It is easy.
Yes.
So now take an example. What is the mass of a molecule? Let's say 10 to the power minus 22 gram. Because for 10 to the power 23 number of 23 molecules, the mass is, let's say if it is 10 gram, and for one particle mass is 10 to the power minus 22 gram, right?
Yes.
So this is m. A is the length of the box, that is, let's say 10 centimeter, and temperature is room temperature 300 Kelvin. Then you can calculate it. It will be around 10 to the power 30. So there are 10 to the power 30 energy states are there for particular one molecule. Okay.
Yes.
So you can write, so if there is 10 to the power, for 10 to the power 23 molecules also, it is huge. For
Yes.
one molecule, the number of 10 to the power 23, you have, let's say, 1 mole of molecule, then also it is very huge, right? So what you can write,
It is because the mass is very small.
yes. So a cube you can take this side, and you can write because these things. This you can write. Okay.
Yes.
So from here, what you can state finally. So you can see, mm, this condition actually, when this condition, how we can do it from here to here. What I have used, we have put a value of a en, right?
Yes.
And that is 3 by 2 kVt.
Yes.
So this condition will be favored when the mass is large, temperature is high, density is low, these things. Then it will be more favored.
Yes.
Okay. So in that case, this condition holds very beautifully. Okay. So that's why this is called actually the classical limit. This condition, high temperature, large mass, low density, this means the classical thing, na? So in classical case,
Yes.
this is this actually followed very well. That's why it is called the classical limit. This is the definition of classical limit. So I'm saying now you can't say when it is quantum to classical, but this is clear. When this is valid, that is definitely under classical case. That is the classical limit actually.
What is the significance of these things? The value of energy is greater than the number density.
Means this n by v, this is density, right? And n is
Yes.
so number of particles are less and states are huge. That means the particles can free to sit anywhere. Okay, that quantum features will not affect. In Bose-Einstein case, what happens basically, they attract and Fermi-Dirac it repels. That's why the single particle state cannot be occupied more than one particle in Fermi-Dirac case. And Bose-Einstein there is a reverse thing. But when these things occur, the energy states are huge. So
In this case,
generally
there
it
is
will,
no possibility of occupying two states for a molecule.
so it will generally follow like Maxwell rules. Actually, in high temperature and high energy, this is actually described by the classical mechanics.
Yes.
Okay. That is the reason. That's why it is called the classical limit. But and this is the calculation. Okay, so I think everything I have covered actually in that course means from where I'm doing this thing, these stuffs. Everything I have covered, but some derivation I skipped. I will share this note. You can go through it. If you have any doubt, you can ask that. But in our next two classes, we will basically discuss uh, that part. You just send me the. Also, I have to arrange your book. I just send me that message that Biman Bagji book. Otherwise, again I will forget.
Okay.
And your exam goes. And this part is clear. Just molecular, the Ising model and cluster expansion. These things in next two class. I will learn. I will study. Then upcoming two classes, I will discuss those things. Okay, then see what happens. And that mail, if I get for extra class, then I will see. I will manage it because one class I did not take.
Okay.
For today's class, if you have any doubt, you can ask. Okay, everything is okay, and this note I will share. So I have not left everything. This PDF now I can upload. Everything I have covered in this PDF. You can take a printout of this. This is very good. This is actually my MSc special course here. From
Which thing?
there, from where I am doing this stuff, this note, statistical thermodynamics note. This was taught
The
in my
note is
MS.
available with you.
Yes, yes, I will say it. But this is MSc level, okay. But everything I've covered, everything you will see, everything. Just one thing I did not cover, that is the Liouville's theorem, continuity equation. Without that, everything I have covered. But in last part, this derivation I did not cover. These derivations are also there. You can go through it, otherwise it's okay. But most of the things are done, so you can readily go with that node. It is written in detail. Everything I have covered, you can have it from this node. I will upload this node. From here you can do it. And my notes are already there, so you can study it properly from here. Okay.
Okay.
Okay, so let me stop the screen sharing first. So next Sunday we will meet in the scheduled time. Probably nothing is there next Sunday. Mm, Just these two things I have to study. And in Biman Bagji's book, probably that is there. Cluster expansion, these things. And you don't know in last week what was done in the class, right?
Yes, I will see in this week.
Okay. Okay, whatever it is, because we have eventually 2 weeks. So I have to discuss these things and it will take 2 weeks. If the time remains there, then we will discuss some question answer from that assignment. That class we missed, na, that part actually left out, that question answer part. That things we will do.
Yes.
But it's okay. Almost we have done a huge thing. That grand canonical, this molecular part we did in the last course, and this part. So everything you have, statistical mechanics we have covered everything. You can say everything we have covered. So you can grasp statistical mechanics very
For
well.
the statistical thermodynamics, we have covered in details.
Everything, and in statistical mechanics also. Okay, that we can do that distribution part. I said this. These things, right? These cumulants, this part I can take. That thing I can do in extra class. Yes, if I still obtain that mail for taking the extra class, in that extra class I will do these moments, cumulants, homogenetic function, cumulative function. These things we can discuss. Random variable, these things. Okay, these things quite advanced, but that is pure statistics. But that is not statistical mechanics. That is statistics. Mm, Properly statistics. That part we can discuss. Then it will be a full packed course. Yeah.
Please send me all the notes you have associated with these topics.
All
Everything.
the notes. All the notes means previous statistical thermodynamics notes you have. And this class note
Yes.
eventually I will upload in the spreadsheet, and only this statistical thermodynamics note from where I am doing this stuff, that I will upload today. Till now I did not upload because I was waiting for completing of this course. Then I said you that after doing this all thing I will upload. So today I will upload that video, and it is written in detail. You can easily follow now. Okay.
Is the class notes available in combined form?
Combined form means
All the pages in one PDF for your
yes,
class note,
yes.
all weeks in one page?
For my case,
Yes. All weeks in one PDF.
not for all weeks, but from 3 to 10, all are in one video. That I can share. Total that I can merge and share to you, but that I can upload in spreadsheet. I will share to you. In spreadsheet, I have to upload week by week.
Okay.
That I will share you separately.
Okay. Thank you.
Okay. Okay. So again, we'll meet in the Sunday. These things. Okay. Thank you for joining.